there's a reason. That's right.
Okay, we'll go ahead and get started here. Thanks everybody for coming to the June 2025 Mount Diablo Astronomical Society General Meeting. Who has been enjoying these great clear skies we've been having recently? Yeah, got a lot of observers out there, and not too hot, not too cold mostly. All right. So we got a couple of announcements before we start. Do we have any new members in the house? Of course, I practice always, and it never works when I get up here. Just move that forward. Okay, any new members? Okay, welcome. If anybody needs to use the bathroom during the meeting, they're through the doors here. We're going to have a break halfway through to get more snacks, so don't overeat right now. For our final community outreach event with the Costa Contra Library, their exploration stations, is going to be this upcoming Wednesday, June 25th at the Hercules Library. So I know these are big events. They have several hundred people that come, so they could use all the help you can have if you have any resources or solar scopes or any kind of presentations. You can give Ken Coates an email or give him a call. Yes, and he's in the back. Ken, how have those events been going?
Great so far. People sign up tomorrow, but also East Bay Astronomical Society is going.
Okay, so East Bay Astronomical Society is helping out. That's awesome. Okay, our next public observing night is Saturday, July 12th, sunset to moonrise. So we can always use help with scopes out there for the general public. Next society night is this upcoming June 28th on the mountain. So hopefully you see a bunch of you up there. And any imagers in the group tonight? Don't forget, we've got our special interest group for the imaging specialist out there. Anybody interested in taking night sky photography, they're always welcoming. You can either email Stu Foreman directly, or he's got that group's IO that you can join and get on the listserv. Next general meeting after tonight will be Tuesday, July 22nd. See if my thing will work now. Okay, so without much further ado, I'd like to present our main speaker for the evening. Dr. Stephen Croft comes from us from UCB and SETI. He is an astrophysicist at the University of California, Berkeley, and a project scientist for the Breakthrough Listen Initiative, the most comprehensive search for extraterrestrial intelligence ever undertaken. He is also an adjunct senior astronomer at the SETI Institute and a senior research fellow at the Department of Physics at the University of Oxford. His work spans time domain astrophysics, you know, that easy stuff, radio and optical astronomy, and the development of advanced algorithms for identifying technosignatures. This is going to be good. In addition to his research, Dr. Croft is active in science communication and education, engaging audiences around the world with the latest developments in the quest to understand our place in the universe. He has talked with us on black holes back in 2017, so we'd like to welcome him again. So give him a large hand.
Thanks very much. Pleasure to be here again. Mixing things up a little bit. We're not going to touch on black holes probably this evening, but I'm going to tell you a little bit about what I've been doing actually really since about 2016, since the Breakthrough Listen initiative launched in 2015 at the Royal Society in London. And I'm going to share my screen. That's all working here. So I'm going to talk a little bit about sort of some of the latest developments in the search for extraterrestrial intelligence, or SETI, as it's often termed, and in particular what we're doing these days with AI, which of course is in the news a lot of late and on everybody's minds. But I wanted to set the scene a little bit by taking us back about 4,500 years when ET visited Earth and built the pyramids in Egypt on the top left here. And then about 3,500 years later, they built a matching set of pyramids on the other side of the Atlantic in the Yucatan Peninsula. In 1947, ET had an engine failure over Roswell, New Mexico, and ended up in a lab here being dissected. That was a bit unfortunate. And then in 2023, the Mexican government was presented with this amazing example of a very well-preserved alien that I think you're probably all very convinced is genuine. And then I think this was in around 2012. This UFO was spotted in Kentucky, and by now you're all, I'm sure, very convinced there is absolute concrete evidence that aliens have visited Earth. These lights in the sky, clearly extraterrestrial visitors, and job done. I think we can just go to the coffee break probably now. I grew up in the UK near Liverpool. Just to add sort of a little bit more evidence, I know you're all convinced, but this is a UFO that was caught on camera by a woman who was outside. It reports here. I'll try and do my best Liverpool accent. I grew up near Liverpool. We were standing there in the backyard having a smoke, and my husband said, "Look at that." The Liverpool Echo reports, and there it is. There's the UFO. Well, this light in the sky in 2012 was actually Google trying to get 2014, I guess. No, 2012. That's right. Trying to get internet to rural areas using big balloons, and there's a lot of these kind of sort of shaky handheld videos. There's a lot of kind of anecdotal reports, but I would suggest that if you see something you don't understand, aliens should not be your first explanation. In fact, they should probably be sort of quite a long way down the list. So I'm not going to sort of find aliens hiding behind the couch cushions. I really think that if we're going to do this scientifically, then we should be able to design scientific experiments that will enable us to determine whether aliens are a likely explanation, and they're usually not, but we might find some interesting other astrophysics along the way, and we might learn something about intelligent life in the universe, which is pretty cool. People have been thinking about this for many years, this question, are we alone in the universe? Are there other minds out there? And even going back 2,000 years, this quote from the philosopher Lucretius, "Nothing in the universe is unique and alone, and therefore in other regions there must be other Earths inhabited by different tribes of men and breeds of beasts." About 1,500 years later, Nicholas of Cusa said, "Life as it exists on Earth in the form of men, animals, and plants is to be found, let us suppose, in the solar and stellar regions. Rather than think that so many stars and parts of the heavens are uninhabited, and that this Earth alone of ours is peopled, we will suppose that in every region there are inhabitants." Now, I note the word "suppose" appears twice here. There's no experiments being proposed here. This is, well, it seems kind of obvious, right, that there's life here on Earth. We look up at the night sky, we see these other stars. Maybe there are other worlds out there. Maybe they're inhabited. And this sort of seemed obvious, I guess. I mean, even sort of around the kind of turn of the Copernican revolution, that there ought to be life beyond Earth, but we didn't really have any ways of testing that. But there's also, as I sort of alluded to, a bunch of hoax. This was the New York Sun moon hoax in 1835, where they alleged that Sir John Herschel at his observatory at the Cape of Good Hope had seen literal moon bats, which I find kind of entertaining. And then more recently, Egypt had to tell Elon Musk, no, the pyramids were not built by aliens. They actually invited him to come and visit himself to demonstrate that. So, there's a lot of kind of people with agendas out there. There's a lot of kind of misinformation. There's a lot, as I say, of sort of dodgy handheld cell phone footage, or videos from military sensors that we don't have access to, and are just sort of presented with a video and told that looked kind of weird to the pilot at the time. But I think we ought to sort of ground ourselves, as I say, in scientific experiments. And really the beginning of the sort of scientific revolution, the beginning of the astronomical revolution, the beginning of the telescopic revolution, 400 years ago, provides some context here. Galileo didn't invent the telescope, but he was one of the first to use it to observe the night sky. And he sketched in his notebook this drawing on the right here, where you'll see the planet Jupiter in the center, and then these stars that appeared to move around that we now know as the 4 Galilean moons of Jupiter. So providing evidence here that things orbited bodies other than the Earth, backing up the idea of the heliocentric theory that things could also go around the sun. There are things going around Jupiter, so maybe things go around bodies other than the Earth. And this, I'll make this point, I think, a few times in this talk, but this was an engineering revolution that led to a paradigm shift, that led to a sort of philosophical revolution, a change in our understanding of our place in the universe that was brought about by engineering. And that thread also runs through the development of the first meter-class telescopes, the 100-inch Hooker telescope here, the largest in the world from 1917 to 1949. used by Edwin Hubble to measure the redshifts of galaxies, and then to determine from this that the universe was expanding, and that these galaxies also that were thought to potentially be within our own galaxy, these spiral nebulae, as they were originally called, were outside our own galaxy, so thereby expanding the scale of the universe as we know it, and also expanding our ideas of our cosmic history and our origins, leading ultimately to the hot Big Bang theory. And so, an engineering development here, again, leading to a paradigm shift. And this is a repeated theme when you get to the discovery of exoplanets. I think probably when everyone in this room was in elementary school, I know certainly speaking for myself, there were 9 planets in the solar system, but none that we knew of elsewhere. And then Pluto got demoted. I'm sorry, I wasn't at that meeting. If anyone's offended about that, we can talk about that a little bit more later. But we now, in exchange, have thousands of catalog planets outside our own solar system, and we infer that planets are pretty much everywhere. And one of the methods that's used, probably many in this audience are familiar, is the transit method. And so you see a planet passing between us and its host star. You see what's called a light curve in the bottom left there. So the light is at some constant level, or roughly constant level. There's also, of course, we know that stars vary in brightness. But as the planet goes around the sun, if it happens to be lined up in its orbit, so that as viewed from Earth, it passes between us and the host star. So we're going to tilt this axis in this simulation here. You see the light is going to drop down, and then as the planet passes, it goes back. And so, this is similar to a transit of Venus. You get that little drop in the light. But we can do this, these precision measurements, with instruments like the Kepler and TESS spacecraft that allow us to measure the properties of these planets, both from the depth of that dip and from the time between these transits, and also the length of the transit. And then we can get more information through other techniques as well that can enable us to determine things like the composition of these objects. We can infer the distance from the host stars, and so we can infer things like surface temperatures. And we can figure out that some of these actually are in what we call the habitable zone of their parent star, the distance between distance out from the host star where liquid water could exist on the surface. So we now have this sort of gallery of exoplanets that have been discovered. This is from an artist based here in the Bay Area, Lynette Cook. So you see the Kepler spacecraft in the middle. And, again, we're not getting images that tell us, this is a gas giant or this is a small rocky world like this. These are artist interpretations, but quite reasonably based on the data that we've got from instruments like Kepler and TESS. Taking pictures of planets is hard. I do think this is a pretty mind-blowing picture of a planet taken by the Cassini spacecraft in our own solar system. It's a mosaic of images, but it is a real photograph taken by this robotic spacecraft that flew 1 billion kilometers out into the outer solar system, turned back, looked at Saturn, backlit by the sun here. You see the rings, you see the gases around it, and the atmosphere of the planet itself. And again, sort of maybe this is not so much of a surprise to many of you in this audience. It maybe is for sort of general public audiences that you're all in this picture, because this is another example of one of these pale blue dot pictures, like the one that Carl Sagan illustrated a few years earlier. But there's the Earth seen from 1 billion kilometers away as this little blue pixel kind of captured between Saturn's rings there. And I show this because, A, it's mind-blowing, B, it's really cool engineering, but C, even from 1 billion kilometers away, a rocky planet like the Earth, almost lost in the sun's glow here, is a single pixel. And so any hope that we have of doing this at distances 10,000 times further away and getting direct images of Earth-like planets are pretty remote. We've only been able to image a handful of exoplanets, and they're much more massive and much further away from their parent star. And so, Earth-like planets in Earth-like orbits, we have to use other techniques to infer their properties. But we can do, we're sort of switching gears here, I guess, back to the search for life. If you're interested in looking for life, going to those exoplanets is going to be hard, but we can do in situ sampling on planets in our own solar system. So Mars being one example where we've sent sort of Mini Cooper-sized robots and now little helicopters to fly around, not doing direct life detection experiments, but searching for organic materials. Mars is a good place to look because we know that liquid water has flowed on the surface in the recent past, and there indeed were vast oceans and lakes in the more distant past. So, in situ sampling for a few places in our own solar system is a good bet. And then we can do remote sensing. So, I alluded to this in terms of kind of getting the light from those exoplanets is really challenging. But with real precision instruments like the ones found on the James Webb Space Telescope, or potentially the proposed 30-meter class telescopes and successors to James Webb as well, you can look at the light from the star as it passes through the atmosphere of a transiting planet. So again, here the planet's going between us and the star. You can look for little dips in that transmitted light that correspond to certain chemicals that are in the atmosphere. And again, with very precise measurements, you can hope to tease out, are there organic materials, or are there so-called biosignatures, so signs of biology that we're using to infer that life is present in the atmospheres of those planets. And again, it's easy enough to do in the solar system because the other planets are relatively close by. And if you were to look at Venus in our solar system in the infrared, you'd see signatures of carbon dioxide. Similarly for Mars, you'd see signatures of carbon dioxide. If you look at Earth, in addition to the CO2, you'll also see ozone, water vapor, methane. You'll see other chemical fingerprints that, again, are not sort of a dead giveaway, right? There could be water vapor there and no life. There could be ozone there and no life. But the combination of these chemical fingerprints are proposed to be used by people that are looking for biosignatures to infer the presence of life in exoplanet atmospheres. This is hard. This is going to require next generation instruments, and the biosignatures that are being proposed are sometimes ambiguous. They're very faint. And so, making a claim, and we can sort of talk about some of the claims that have been made, including sort of fairly recently for the existence of life or biosignatures on exoplanets, should always be taken with a grain of salt. These are really hard measurements to make. They can only be done for a handful of nearby stars and their planetary systems. And so this leads us to technosignatures. And so we're sort of deliberately using this term. SETI is a term that many people are familiar with, the search for extraterrestrial intelligence. But we're sort of shifting our language a little bit, kind of to directly emphasize the fact that this is complementary to these searches for biosignatures. So a biosignature is a sign of biology as a proxy for life. A technosignature is some sign of technology as a proxy for intelligence, or for engineers, if you like, for somebody who's constructed something artificial. And it could be powerful radio transmitters, it could be powerful lasers, it could perhaps a bit more sort of fancifully and extrapolating a little bit further forward be things like giant megastructures in orbit around stars. Could we look for signatures of these things? Could we find them, and how far out what might we hope to see some of these technosignatures? And is this a good game to play in addition to playing the biosignatures game? I would argue it is, and that these two things are sort of complementary, and they come under the overall umbrella of astrobiology, the search for biology beyond Earth, which is a real priority for NASA and for other federal agencies in the next few years. So how good you are at reading cursive. Most of the undergraduate students that I get coming in at Berkeley now are not, so I'll just read this for you just in case. Undoubtedly, and this is a quote from a letter from Nikola Tesla, by the way, in 1937, and Tesla says, "Undoubtedly there are myriads of planets in the universe which were, are, or will be abodes of life in its highest forms. The same formative principles must be operative in the building up of the bodies of the inhabitants, and their perceptions of the external world must be closely similar to ours. It is highly probable that many are as far or even more advanced than ourselves. Codes for communication and mutual understanding can be readily formulated on the basis of commonly perceived universal truths." Tesla then goes on to say, "By my inventions, it has become possible to transmit considerable amounts of energy at distances of thousands of light years, and if received, it can be easily detected in many ways." Now, this is really prescient from somebody writing in 1937 saying these radio waves could be detected at thousands of light years, and actually a back-of-the-envelope calculation shows you that that's about what we can hope for. With Earth's brightest transmitters, something like the now defunct Arecibo radio telescope and the transmitter that it had on that big dish, and then something similar on the other end as a receiver, you could communicate at thousands of light years across the galaxy. And so this is worthwhile doing, and that volume will contain millions of stars. So it's, even if technosignatures are a lot rarer than biosignatures, we have many more targets that we can potentially look at. But it took until 1960 for Frank Drake, sometimes called the father of modern SETI, to do the first technosignature search. using the 85-foot Tatel telescope at the Green Bank Observatory in 1960. Frank sadly passed away a few years back. He was still active in SETI and with the SETI Institute, even in the later years of his life. And he carried out a project called Project Ozma, where he borrowed this piece of equipment here in the bottom right to do a search at a frequency of 1420 megahertz. This is, again, I won't get into this now. We can talk about this maybe in the Q&A. Why is 1420 megahertz sort of a good frequency to look at? Well, for Frank, it was a good frequency because he happened to have a receiver that he could borrow that was tuned to this frequency. There was nothing really kind of more, philosophical about this. And so you see in the logbook there on the left, a few observations of Project Ozma, named after the princess in The Wizard of Oz. And this receiver, so it's a single channel radio receiver, and Frank looked at 2 stars. And the second star that he looked at, they found something and they got quite excited and they said, can it really be this easy to look for aliens? And that was, I think, the first sort of false positive in a SETI search. It was the first SETI search, the first false positive in a SETI search. And we're still dealing with those kind of false positives today. And the reason why is because the motivation for us to search is here on Earth. We have technology. We have cell phones, we have Wi-Fi. I mean, Frank didn't in 1960, but there were still radio transmitting devices. And so the idea that, well, ET might develop radio transmitters too is a good reason to go look for them, but it also makes it really challenging because we're looking for these radio transmitters in this sort of, sea of our own radio noise. And Frank hung another antenna out of the window of the control room at the Tatel telescope, picked up the same signal that he was seeing coming in through the telescope itself and realized, okay, this is local. This is not coming from the star that I'm pointed at. This is local radio frequency interference, or RFI as we call it today. And this bedevils radio astronomy experiments in general, more and more as there's more and more radio transmitters out there, but SETI experiments in particular. RFI is something that will come up again and again. As I just alluded to, it's hard, but it's not necessarily, a silly thing to do to go out and look for technosignatures because we're in such a target-rich environment. You look up at the night sky, here's the Milky Way galaxy, and pretty much every star that you look at, we now know has planets going around it. Again, we've learned that since I was in elementary school. I think this is a really cool result. So maybe 20 or 40 billion planets like Earth in our own galaxy alone. So that's a lot of targets. And then, as I mentioned, many of them in the habitable zone of their parent stars. And so this region shown in green, in our own solar system in the middle there, Venus towards the inner edge of the habitable zone, now too hot for life to exist on the surface, at least life as we know it, because of the runaway greenhouse effect. Mars towards the outer edge, probably too cold because it's not massive enough to have held on to most of its atmosphere, but Earth, nicely in the middle there. And then in other systems like the Kepler-22 system, we see evidence of super-Earths like Kepler-22b, so a smallish rocky planet that's in the habitable zone. These are good places to look for biosignatures, but potentially also good places to focus a technosignature search. And this isn't even to mention the icy moons around the gas giants in our own solar system. These may exist in other solar systems too. So this is not in the traditional definition of the habitable zone. There's no liquid water on the surface, but we infer that there's a liquid ocean underneath the ice crust of these moons. And there are geysers that are gushing this material into space through cracks in these ice crusts. There are proposed missions to send probes out there that will fly through these plumes and sample them and look for organic materials. And so again, sort of in situ biosignature searches in our own solar system, but also kind of a reminder that there are many other places to look for life other than habitable zone exoplanets. And then you can expand, from our own galaxy to the universe as a whole. The Hubble Ultra Deep Field, this is a grain of sand sized region of the sky, a grain of sand held at arm's length. The star in the middle, you see the diffraction spikes there. That star is about 10,000 times too faint to be seen with the naked eye, and that's about the brightest thing in the image. And so you're looking at a grain of sand-sized region of the sky that would appear completely dark to your unaided eye. And here it is when the Hubble telescope stared at it for 11 days. Here's what it saw. And pretty much everything in here is a galaxy. So there's a few stars in the foreground. There's about 10,000 galaxies going into the distant universe as far as the telescope can see, to distances of billions of light years. And each of those galaxies with billions or tens of billions, even hundreds of billions of stars, and presumably many of them, at least in the more recent universe, with planets and maybe with life, right? So you do a little bit of back of the envelope math, maybe 10 to the 22 places where life could arise in the universe. And so I think the odds are pretty good. So where is everybody? The Fermi paradox is probably not originally due to Enrico Fermi, and it's not really a paradox, but it is a bit of a head scratcher, right? If there are all those places where life could arise, if the ingredients for life are everywhere, if the conditions for life are everywhere, why is the best evidence that we have for ET, a shaky cell phone a video from a woman in her backyard in Liverpool? Well, Frank was pretty busy in the 1960s, and one other thing that he came up with, aside from the first SETI search, was the Drake equation, formulated in 1961 at a meeting again at the Green Bank Observatory. This sort of at the time was a pretty bold sort of attempt to parameterize a bunch of things that we didn't know. So N, the number on the left there, sometimes called Drake's N, is the number of communicating civilizations in the galaxy right now. And so this is sort of the number of people that we could hope to have a conversation with. And I would define this sort of further as saying, if you're doing a radio SETI search, then N is the number of radio transmitting civilizations in the galaxy right now. If you're doing a laser SETI search, it's the number of civilizations that are using lasers to try and communicate. And as somebody who came up to me after a public talk and had maybe been watching a little bit too much Star Trek said, can you do a tachyon search? I think they're probably using tachyons. I said, if you can build me a tachyon detector, I will happily put it on the Green Bank telescope. And so if N is your tachyon experiment, then feel free to do that as well. But I think I'm thinking in the context of radio here, at least for now, and I think Frank probably was as well, having done that radio experiment the year prior. And so the numbers on the right here are R star, which is the rate at which stars are being formed in the galaxy. So the number of stars born per year. It'll become clear why we use that rather than just a number of stars when we work our way through these other terms. F sub P is the fraction of those stars that have planets. N sub E is the number of Earth-like planets per star that has planets. F sub L is the fraction of those planets that have life. F sub I is the fraction of those planets that have intelligence. F sub C is the fraction of those planets that develop communication. And again, this could be radio communication if you like. And L is the lifetime of that technology in years. And so that lifetime cancels out the rate of star formation per year on the left, and you end up just with a number. So you've got a rate multiplied by some fractions, multiplied by a measurement in years, and you get a number on the left there. Again, the number of sort of actively communicating civilizations in the galaxy right now. So I'll go through this again. Some of you are probably more familiar with this than others. But the only number that Frank knew with any confidence in 1961 was the rate at which stars were formed in the galaxy, and it's something like 5. We'll sort of give or take it somewhere between 1 and 10. Frank didn't know what the fraction of stars with planets were back then, but again, if you're paying attention, you'd know now that that's something like 100%, maybe a little less, but close to 100% of stars we now think have planets. And again, if you're paying attention, about 1 in 5 planets are habitable zone planets, so we'll multiply that by 1/5. Again, the number of planets per star that has planets that are in the habitable zone. We still don't know what fraction of habitable planets have life, so that's still a big question mark. We don't know what the fraction of planets with life that develop intelligence is, so that's still a big question mark. We don't know, once you have intelligence, is communication inevitable? Is radio technology inevitable, for example? So we don't know what that one is either. And then the lifetime of the technology, or even the lifetime of the parent civilization, again, if you've been following the news recently, you might think that our odds are not very good, and maybe Drake's L is pretty short. But for a radio transmitting civilization, we've had radio for 100 years, so you might sort of drop in 100 years there. Maybe you think we'll have it for 1,000 years overall. You might drop in 1,000 years. But one of the interesting things here, I've sort of set this up in a bit of a contrived way, right? We've got 5 stars per year, 100% of them with planets, 1/5 of them with a habitable zone planet. And if you're an optimist, you might say, well, yeah, the ingredients for life are everywhere. The conditions for life are everywhere. let's assume that life arises everywhere that it can. This is the Copernican principle, right? We're not in some weird place. Like, we only have one example here on Earth of life. Let us suppose that life arises everywhere. And then intelligence, I mean, it seems like it's maybe a hard step on Earth. Life took hold fairly early on in the Earth's history, and it took billions of years for intelligence to develop. But let's assume that it's inevitable, I guess, if you're an optimist, and set that equal to 1. And then, as I say, maybe everybody develops radio communication. It's a sensible way of sending information over long distances. It's pretty energy efficient, certainly compared to gravitational waves, where you've got to get a couple of neutron stars and smash them together. So let's assume that radio waves are a good bet, and that F sub c is 1 as well. And then the way that I've set this up, I mean, even if you remember your elementary school math, you can multiply those numbers together on the right, and you come up with n equals L, which is sort of the optimist Drake equation. And all that's saying is the number of transmitting civilizations in the galaxy right now is just set by the lifetime of that communication. Again, if you're an optimist about the chances of life arising. So if there's 100 years of radio technology here on Earth, there should be 100 radio transmitting civilizations in the galaxy right now, and we should go out and look for them. Frank, it turns out, was an optimist, because this was his license plate when he was at the University of California, Santa Cruz, N equals L. So Frank was an optimist about the chances for life, and I think that means that we probably should be as well. So I mentioned again in 2015, there was this sort of shot in the arm for technosignature searches. The Breakthrough Listen project was launched at the Royal Society in London with a pledge of $100 million. It's a sort of a ballpark figure. I guess I'm waving my arms around just as the presenter was. I think she was asking me at the time, what would the aliens look like? And I was a little sort of bemused by this question, as you can see on the right there. I think the $100 million was the thing that got Fox Business News' attention. So a lot of media attention, a lot of interest in the search for extraterrestrial intelligence. And I'll tell you a little bit about what we've been doing in the last 10 or 11 years, 10 years, with just coming up on 10 years actually with Breakthrough Listen. So we're using a telescope still at the Green Bank Observatory. So Frank used the 85-foot Tatel telescope. We're using the sort of 300-ish foot Green Bank telescope, 100-meter dish, collecting area the size of 2 football fields. You can get an idea of the scale because there are some guys that had just rappelled down on ropes from underneath the telescope. You can just see on the ground there and maybe just about make out the ropes, and some full-size trucks in there when I took this picture. And that's our chief engineer, Dave McMahon, in the foreground here also, to kind of help you with the scale of this thing. It's the largest movable structure on land, asterisk. They slid in a big sarcophagus over the remains of the Chernobyl nuclear reactor, which technically is larger, but they just slid that in once and put it there. This thing I can control from this laptop, which is kind of cool. So 7,000 tons of metal in rural West Virginia. And it's doing a bunch of SETI work as part of the Breakthrough Listen program. So we got a big dish. We need big computers. So Frank had this single channel receiver, right, that he looked at 2 stars. We now have 12 gigahertz of bandwidth from this thing with 3 hertz resolution. So, if that's sort of not really meaningful to you, it just means that we're looking at billions of channels at a time. And we have a ton of storage, something like 8,000 times as much storage as I have here on this laptop. And with a data rate streaming out of this thing that would burn through your home internet connection pretty quick. It's about 1,000 times what your typical home internet connection will be able to ingest. And right now, well, not right now, it's down for maintenance during the summer, but with the Green Bank telescope, we're doing about 10 hours of observing per week. And we're storing huge amounts of data. We actually have to average down the data that we're taking. If you're doing some back of the envelope math and realizing that we would fill the disks up a lot quicker than this suggests, we're archiving sort of a small fraction of the data, but we're doing a really comprehensive search is what you should take home from this compared to what Frank was able to do in 1960. And this again is really just due to engineering. It's due to Moore's law, the increase in the availability of computing power and storage doubling every 18 months or so. And so we're really able to do searches that would have been kind of mind-blowing to Frank. Well, I know were mind-blowing to him because I spoke with him about it sort of more recently before he passed away. So this is, really, really, really cool stuff. So what do you get out of one of these computers in one of these racks? So we popped a little hard drive out of there just to show you these things are full of hard drives. But that computer is one of 64 that we have at Green Bank. And the data that you get out looks like the image on the right here. Has anybody here, just curious, played with software-defined radio at all? I'm guessing not. So these are little $30 dongles that you can buy on Amazon, and you can do kind of amateur radio astronomy. I mean, you can hook these up to a horn antenna and map hydrogen in the galaxy. You can also use them for listening to the radio or picking up transponders from passing planes. There's a bunch of stuff. So it's GNU radio, GNU radio, or software-defined radio, the things to look for here. We're using this in our undergraduate education, teaching the students about radio astronomy. It's pretty cool. And the data that you get out of that looks very similar to the data that we get out of this computer cluster at Green Bank. And all as you're seeing on the right here is what we call a spectrogram or a dynamic spectrum. So if you're familiar with spectroscopy, right, you split the light up into its constituent wavelengths or frequencies, and so that's shown on the horizontal axis, the frequency here, and then on the vertical axis is time. And so, again, sort of Frank had this one channel. We have billions of channels. There's actually only a few 100 million channels shown here, and obviously, you need to zoom in to see them individually. Ignore the black lines here, but what you're seeing in the colors, the greens and yellows and blues, is the intensity of the signal that is picked up by the telescope as a function of frequency on the horizontal axis and time on the vertical axis. And so this is an observation of a star from the Hipparcos catalog. We looked at it for 5 minutes. We looked at it over 187.5 megahertz in frequency. So, if you listen to your local public radio station, I guess probably KQED out here is 88.5, even this side of the hills. We're looking up here at 2400 megahertz, not at 88.5 megahertz. And we're tuning to a much broader bandwidth than your FM radio tunes to. So we're tuning again to millions of 3 hertz wide channels at a time. And we're picking up some signals, these little squiggles that you see there. So ignore kind of the vertical black lines, but the little squiggles that you see kind of over to the left there, those are real signals that are picked up by the telescope. The problem is, even though we're in the National Radio Quiet Zone, so Green Bank is in the middle of this kind of federally mandated zone here in West Virginia, I think mainly to protect, there was an NSA listening station over the hill at Sugar Grove, and I think they were probably more interested in the NSA having clear airwaves than they were with the radio astronomers. But the feds have been good in terms of protecting this area from radio frequency interference, except people don't turn their cell phones off when they come to the telescope. They're maybe just taking a picture of the telescope and they forgot to put it in airplane mode. There's still planes that are going overhead. I'm not sure there are so many garage door openers over there, but there's still, Wi-Fi, again, particularly on cell phones. There's now Starlink satellites overhead. It's great if you want internet in the middle of nowhere, except if you don't want internet in the middle of nowhere, like we don't want at Green Bank. And then, again, I can tell you a story in the Q&A about impatient people microwaving their lunch at the Parkes Radio Telescope in Australia, pushing the door open button, a little burst of microwaves comes out, the telescope picks it up, and everybody gets excited that they've detected something. So, the bane of our lives is the technology that we have here, right? Again, as I alluded to, the fact that we have all of this radio emitting stuff that motivates us to go and see if other people are doing this, but really is kind of an issue for us when we're doing these searches. And, in particular, again, if you think about Frank's searches done at 1420 megahertz, so I'll zoom into this table of frequency allocations here, and you'll see, the FCC has helpfully reserved this little band around 1420 megahertz for radio astronomy, and this little band up here around 1660 megahertz and a few other bands. But when you're tuning to 1 billion radio channels at a time, we're not staying in our lane anymore. Oops, I've lured the camera. So we're straying into picking up signals from aeronautical radio navigation, from mobile, from a lot of kind of satellite stuff, basically. And again, even in the radio quiet zone, there are satellites going overhead, and that's a real problem. And I'd say it's a real needle in a haystack problem, and that is the point at which I had said we're going to break for coffee. So we'll ignore the phone that is apparently now possessed by some alien intelligence that is kind of walking its way across the table here, and I'll let you go get some snacks, and then we'll come back and figure out how we're going to deal with this and with that. Thanks.
All right, thanks. Let's go ahead and resume this wonderful lecture.
All right, thank you. Yeah, so when we left, we had our heads buried in a haystack looking for a needle. The problem is here, right, we don't know if there's a needle in the haystack, and we don't really know what the needle looks like. We don't know if it's a sewing needle, a knitting needle, or the Seattle Space Needle. So we're trying to dig around in this haystack. And our only hope really is, well, let's just get rid of as much of the hay as we can. So the hay here being this RFI, this radio frequency interference, all the stuff from our devices. And I want to be pretty confident if I'm kind of shoveling away at this haystack that I'm not throwing away anything interesting. And this is the real challenge. So this is the challenge that we're going to be addressing in the rest of the talk. So one way of sort of isolating a signal, if you're thinking about a sound, would be to use a directional microphone. And so if I'm pointing at somebody in the audience that I'm interested in picking up their conversation, let's say you're all kind of chatting away and I'm just interested in picking up one person's conversation, I could point the directional microphone at them, then I could point it somewhere else, then I point it back at the person that I'm interested in, back at somebody else, and I compare the signals that I'm getting when the microphone is pointed at the target versus when it's pointed elsewhere. And we can do the same thing with a big radio dish like the Green Bank telescope. And so the Green Bank telescope is primarily sensitive to this region, the primary beam. So I showed you the Hubble Ultra Deep Field earlier, all of those galaxies. The primary beam of the GBT is several times bigger than the Hubble field at the frequencies that we're operating at. So you're just seeing that sort of basically as a single pixel. It's not very high resolution, but it's picking up any signals that are coming from that area of the sky. And then by physically moving the telescope around, by pointing it in different locations, comparing the signals on target and off target that we're getting from the receiver, then we can filter out, just as Frank did in 1960, the signals, hopefully, that are coming locally, and we can say, okay, we're going to throw those away. And so I have a little simulation. So this is with the free software Stellarium that probably many of you are familiar with here. You can activate the satellite catalog in Stellarium, and it'll show you a bunch of satellites in low Earth orbit in particular. And what I've done here, you're not seeing sort of very high resolution on the screen, but it doesn't matter particularly for this illustration. You'll see a little reticle in the middle there that's pointed at Vega. And when I start the animation, you'll see we're now going to point somewhere else. And then we're going to point back at Vega again. And then we're going to point at another star nearby again. We're going to point back at Vega a third time, and we're going to point off target again a third time. And then we're going to zoom around here, and you'll see the geosynchronous satellite belt here on the right. You'll see a bunch of satellites in low Earth orbit that are whizzing by. And you'll see there the target star, Procyon, that we're on and off target again there. Occasionally, a satellite will come really close to that target, and so we'll maybe pick up a signal from the satellite that's going past. But again, I'll play this again. You'll see the satellites moving. Certainly the satellites that are in low Earth orbit that are moving pretty fast. You'll see the star moving across the sky. And we're doing these on-off pointing. So typically 5 minutes on the star, 5 minutes off the star, times 3 iterations. We call this a cadence. But even with the geosync belt here, because the star is moving, right, the star is fixed in right ascension and declination, but it's not fixed in azimuth and altitude. The geosync belt is fixed in azimuth and altitude. And so that means that as the star moves, we're typically not going to land on the same satellite 3 times in a row. And so you're not going to get sort of a confusing, a confounding signal in your 3 on observations that is not absent in the 3 off observations. And so this is a spatial filter that we use to basically try and kind of winnow down this haystack again. Another filter that we can use is what we call the Doppler filter. And that suggests you stand in the path of an ambulance to experience the Doppler effect. Again, I think you're sort of mostly familiar with this, certainly from the idea of redshift, right? That if something is moving away from you, then the light is shifted towards lower frequencies, towards the red end of the spectrum. Similarly, the sound from a siren will be shifted towards lower sound frequencies, towards the lower end of the sound spectrum. And if it's coming towards you, then it's blue shifted, right? And we're familiar with this Doppler shift. Red shift moving away, blue shift moving towards. You're also probably familiar with Doppler drifts. Maybe not in the context of astronomy. You're more used to hearing about Doppler shifts in astronomy. But a Doppler drift, if you've stood more sensibly on the sidewalk as an ambulance goes past, then you'll have heard that change in frequency over time. As it goes past you, right? The pitch changes because the relative velocity is changing as the ambulance is going past you. So that's an acceleration. A Doppler acceleration results in a change in frequency over time. So not a shift, just a linear shift to the red or the blue, a change in frequency. And we can take advantage of this because we have radio telescopes that are like the Green Bank Telescope and Parkes Telescope on a planet that's rotating. That planet is going around our star, the sun. And if somebody else has a transmitter on their rotating planet and it's going around their star, then there's going to be a relative acceleration between those two transmitters. So if I have a transmitter that is transmitting at a constant frequency, so a constant tone, like just kind of hitting a key on a piano or playing a whistle or whatever, I can filter that out because that constant frequency over time is a signature of something that's not accelerating with respect to my telescope. So I only want to preserve things that are changing in frequency with time. And so that's another filter, this Doppler filter. So I'm looking for Doppler accelerations. I'm looking for this relative motion between the transmitter and the receiver. And I combine that Doppler filter with a spatial filter, and I got a pretty good way of finding signals that look interesting. So here's some real data from the Green Bank Telescope. So I mentioned that we do these cadences, right? We do, it's not the animation, we do an on observation, off, on, off, on, off. So the on scans are scans of this, the star from the TESS input catalog with a long phone number there at the top. And then we alternate that with scans of these off-target stars. So the A star is TIC whatever, and then the B stars are 3 stars from the Hipparcos catalog. So again, you're seeing these dynamic spectra here. So frequency on the horizontal axis, time on the vertical axis. So these are 6 5-minute scans stacked up to form 30 minutes of observing time. And the green signal in the middle there is the signal where this red dashed line is kind of guiding your eye to the fact that there's a Doppler drifting signal here, right? So over 30 minutes of time, this thing is changing in frequency by, looks like about 50 hertz. So that's about sort of 20 or so of our channels, and so we can pick up that shift in frequency, and we can say we're not going to throw this one out in the Doppler filter. It looks like it's not a constant frequency. If it was a vertical line here, we'd throw it away. We'd say this thing is always on at the same frequency. We're still going to throw this one out though because it's there whether we're looking at our target or looking off the target, and so it fails the spatial filter and gets thrown away. Doesn't pass through. So we got rid of a bunch of the haystack here, even for signals that look like they're drifting. But here's an interesting one. We look at the target, and it's there, this clear yellow sort of drifting line in the first one. We look off target, and it's gone. There's some sort of broadband interference there, that kind of yellow band across the bottom, but we're going to ignore that because that's not obviously the same signal as this drifting signal. We look back on target, and it's there. We look off target, and it's gone. Back on target, it's there. Off target, it's gone. The signal was found by a high school teacher working with me a couple of summers ago, Ilan Levy, and I told him, Ilan, congratulations, you have discovered extraterrestrial intelligence. That was a pretty exciting day for Ilan. Unfortunately, it was not aliens, it was Voyager 1. So, it's extraterrestrial. It's engineered. It's 20 billion kilometers away. It's pretty cool that we can do this. I knew where the telescope was pointed at the time. It was pointed at Voyager 1 and then away from Voyager 1 and back at Voyager 1. But 20 billion kilometers away, there's a 23-watt transmitter on this thing. So this is the same power as the light in your refrigerator at home. It has a 4-meter antenna. And so, it looks a lot brighter when you point at this thing. It looks like it's a megawatt transmitter to the telescope on Earth. But that's still, pretty impressive to get this at that distance. And it's coming through loud and clear in our scans here. And it passes, this is the important thing, it passes through the filter. And if you know a little bit of Python, my students, I usually point them to this Python notebook where you can go and download the data from the Green Bank Telescope. You can run it through the code that we use, and you can have it spit out, hey, here's something that you should be interested in. And it's a bona fide techno-signature, right? This is a sign of technology that's coming here from a distance of 20 billion kilometers. We only have to do that at distances of 10,000 times further away. Okay, only have to do it 10,000 times further away. Well, we can build transmitters that are more powerful than 23 watts. We can build dishes that are bigger than 4 meters. And again, you do the back of the envelope like Tesla had obviously done in 1937, and you realize, yeah, you could do this at 1,000 light years, with a big dish on each end, with nothing more advanced than 20th century technology. So that's pretty cool. So we should do this. We should do this for a bunch of stars and see if we see anything like this. Spoiler alert, we haven't seen anything like this, certainly kind of this clear in all of the targets that we've looked at. Otherwise, first of all, I'd have a Nobel Prize in a parking space in front of the building on the Berkeley campus where I work. And secondly, you'd have read about this in the media. But we're still working hard. And one of the things we're doing, this will be probably the most complicated plot that I'm going to show today. So if you're a little bit bewildered by this, don't worry. This was from a paper from a student of mine, Carmen Chosa. So she was in our undergraduate intern program at Berkeley a couple of years back and is now in the PhD program at Oxford. Very impressed with sort of where our students end up. They're really doing great stuff. And so in her paper that she led based on work that she'd done with me in 2024, she plotted up some points on this plot. And this is, again, sort of a complicated plot, but all I want you to take home from this is that faint things are towards the left-hand side of the plot, bright things are towards the right-hand side of the plot, things that are rare are towards the bottom, things that are common are towards the top. And Carmen added these points that are kind of, I'm worried this thing is going to walk away, but okay. These colored points down in the bottom right here. She looked at galaxies, at 97 nearby galaxies. And so here, okay, we're not even trying to say are the radio transmitters around nearby stars. Here we're trying to say, has anyone out there built a radio transmitter that's bright enough to bridge, millions of light years between galaxies? And you're thinking, Steve, that's nuts. Why would you try and do that when, we haven't even succeeded around nearby stars? Well, the answer is that if you look at a galaxy and you put it in the beam of the Green Bank telescope, you're looking at billions of stars at a time. So you only need, 1 in a billion of those to have a really powerful radio transmitter that's pointed in our direction. And, you've captured that. And so Carmen, by looking at 97 nearby galaxies, was able to put some constraints on very rare transmitters, but they have to be really bright. And so that's why these points are down in the bottom right-hand side of the plot here. But we can also look at nearby stars, and here we can see things, transmitters that are more intrinsically faint. And so, I mentioned that the Voyager transmitter looks like a 1 megawatt transmitter. So here we're looking at things that are brighter than that. They're more like the Arecibo transmitter, which looks like a 10 to the 13 watt transmitter. But we can do that for kind of 1,000 nearby stars. And so the points in the top left there are what happens when you look at 1,000 stars and you find things that are potentially intrinsically a lot fainter than they would need to be if they were coming from nearby galaxies. And so we can combine all of these points, and Carmen does this in this plot, right? And she can tell you, okay, bright transmitters must be really, really rare in our local universe. Faint transmitters, there are fewer than 1 in 1,000 of them, that are stars that are kind of pointed in our direction, that are transmitting while we're doing this experiment. And so we can rule out this region, basically the region kind of above all of these points towards the upper right. And we can say, there were no transmitters when we did our surveys at the frequencies that we were looking at that were pointed in our direction, that we're doing, that were radio transmitting at the time. And so, yeah.
Type 2 and type 1, are you talking about supernovae?
No, so yeah, I should have mentioned that. So this is Kardashev type. So if you're familiar with the Kardashev scale, basically type 1 is taking all of the energy from a star like the sun and using it to power your technology. So building a single radio transmitter that takes the entire energy from the sun that's falling on Earth, I should say. That's type 1. So if you covered the Earth with solar panels and then powered that up with a radio transmitter. Type 2 is take all of the energy from the star. So take, everything that's coming out of the sun and hook that up.
So the horizontal axis power,
Yep.
and then the vertical axis, and it says rare and common.
Yeah.
Transmitter rate. You're talking about actual radio waves that you're detecting.
So it's sort of funny units, and that's sort of why I didn't kind of really get into this, but you can think of it as sort of number of transmitters per star, and it's in log units. And so, -3 on that axis would be 1 in 1,000. That's a measurement from the surveys that we've done. So there's a bunch of surveys from the literature here. You can see even going back to 1993, one of them with the co-author Sagan, whose name might ring a bell to some here. And so you go out and you look at a bunch of stars. You don't see anything because nobody has seen any, confirmed technosignatures to date. And then you say there are fewer than, 1 per n, transmitters out there. It's a little bit like, here we are in the Wildlife Museum. I might as well connect you to this. You're looking for, snow leopards in the Himalayas. You don't just go and camp out in your tent, stick your head out once a day, and then, close the zipper and say, I didn't see any snow leopards today. So no snow leopards in the Himalayas, right? You do a drone survey. You look for, the remains of their meals. You look for scratch marks on trees. You do a bunch of stuff. And then if you see nothing, then you say, well, there are fewer than, 2 snow leopards per square kilometer or whatever number you come up with. And so that's what we do here. We look in a bunch of places. We look at a lot of stars at one time when we do this survey of nearby galaxies. We look at a few stars really carefully in the nearby universe when we do our survey of nearby stars. And then we compute the power that the transmitters would need to be to reach us from those distances. And we plot those up on this plot. And we haven't looked down in the bottom left region of this plot. And again, this is, I think I have this little animation here, right? So, this is where we are with our most powerful transmitters on Earth, is where that blue arrow is. And so we're saying, it's a pretty weak constraint. For Earth-like transmitters that are pointed in our direction, so somebody deliberately, transmitting in our direction, we can only say, well, fewer than 1 per 1,000 stars. So we've not done, the take home here is, we're doing a much better job of searching than Frank was in 1960, but we're still not doing a very good job. There's a lot more space to explore. And this is one possible explanation for the Fermi paradox that we just haven't looked hard enough yet. But maybe we're also sort of not looking smart enough. And I like this cartoon from New Scientist. Professor makes the horrifying discovery. The messages sent across the universe by advanced alien civilizations have been going into junk mail. So, maybe we're throwing the needle away with a haystack, and we've got to be smarter about how we're doing that filtering. There's this analogy from our colleague Jill Tarter. Jill is one of the pioneers of radio astronomy. She still lives up in the Berkeley Hills. We still see her at meetings occasionally. And Jill has this nice analogy where she says, if you scooped a glass of water out of the ocean, you saw no fish in the glass, you'll be silly to say there are therefore no fish in the ocean because they saw none in the glass. This is the same point that I'm making about, making sure you've done a comprehensive survey. So you could get a bigger bucket, so you could get a hot tub, and we've done about sort of 1 hot tub or small swimming pool's worth of sampling now, from that plot that I just showed you. Or you could use a different technique. And my argument is, if you put that water under a microscope, it's full of life. You just were looking for the wrong thing. You're looking for fish, but there's microbes. We need sort of better technology. We need better signal detectors. And one thing, I tell our summer interns is, like AI is a really good tool to use for this. Google has figured out how to find ET. Here's a screen grab on the left here. You go and type it into Google image search, and it finds a bunch of images of ET. Unfortunately, then when you use those images to train an AI image generation algorithm like Midjourney or the algorithms that power like ChatGPT's image generation, you say, show me ET, it says ET is a lizard wearing a hoodie that rides a bicycle. And just sort of taking a step back here, this is a big problem with AI, right? AI is biased. And it's biased because we feed it training data. We feed it sort of, in this case, human labeled training data. And we say, this is what ET looks like. And it says, got it, okay, I can generate that for you. This is a problem if you're using AI to determine who gets a bank loan, who gets a job, who is a security risk. There's a lot of things where AI is going to come and make a lot of decisions in our day-to-day lives. And I know there's a lot of folks thinking about this, including a lot of folks who are working in developing these systems and these algorithms. But this is a real kind of cautionary note for me that AI learns human biases and sort of bakes them in. And we've got to be careful about that when we're doing science with artificial intelligence and machine learning as well. We've got to make sure that our training data really reflects the things that we're trying to find. So sort of cautionary tale here. But we've been using it. And again, I'm getting a little bit of gray in my beard here, so I'm not the kind of guy, who's going to go and sort of hack away at these machine learning algorithms. I have students, one of them, Peter Ma, who started working with us when he was a high school student. carried on during his undergrad at the University of Toronto, and now is in the astronomy program at UC Berkeley. So also very proud of Peter. You'll see his face popping up a couple of times in these slides as well. And Peter used a machine learning tool called an autoencoder, which is illustrated here on the bottom. And I'm just going to sort of briefly describe what this does. So you can take a set of handwritten numbers. For example, here's a number 4 on the left. You feed it into an encoder. Some sort of magic takes place in the encoder, and it reduces it down to this compressed vector in the middle here. And this looks kind of weird, but it's just a representation of this number in a sort of compressed space, what we call a latent space. You feed that vector into a decoder, and it spits out a handwritten number 4. And you're thinking, okay, Steve, like why do I want a machine that I feed the number 4 into, and it pops the number 4 out? Well, the reason is because the training stage, the point at which you have this training data and you're training the algorithm, is doing something to what we call minimizing the loss between the output and the input. And so initially you feed this in, you get junk out of the other side, and then you tweak some things, and you get something that looks more and more like the input. And once you get something that looks like a 4 out on the right, you can be confident that this compressed representation in the middle represents the essence of what it is to be a number 4. And then you train it on numbers 5 and 6 and 7 and so on. You feed those in, and once you've trained it to the point at which you're getting what you expect out of the right-hand side, then you just take that little slice out of the middle. This is now my latent representation of the thing that I'm interested in, and I can do all sorts of clever things with that, including looking for numbers that look similar, for example. So somebody might draw their 7 a little bit differently. Maybe they draw a bar across their 7, or the horizontal stroke is at a bit of an angle. But it's going to look more similar to another handwritten 7 than it will to a number 9. And so we can do all of this kind of clever stuff in this sort of latent space, basically, with these autoencoders. And I'm trying to give you sort of really just kind of a vague appreciation of what's going on here, so don't sort of sweat the details. But one thing that Peter was able to do was to say, okay, I'm going to take some simulated signals like the one on the left here, which if you're paying attention, you will say, okay, that's Doppler drifting, but it's there on the ons and the offs. That's not a good SETI candidate. And then we can take examples like the one on the right there, where there's this drifting signal that you see kind of close to the middle. There's a bunch of other interference there. So, we're now doing this in a noisy environment compared to that nice kind of clean sample of Voyager 1. And then Peter can train this infrastructure to tell the difference between things on the right and things on the left, and then deploy it and find real things in real data that the algorithm wasn't trained on. And he found 8 candidates. I mean, we don't think these are aliens. Again, the standard of proof is higher, but 8 things that came out of our data analysis got the attention of space.com, which was pretty cool. And so this is finding things that were missed by the existing algorithms, and in particular because they're in this sort of noisy environment with a bunch of RFI. Google also knows how to do reverse image search, and so you feed in an image of ET and then it finds things that look like that, or you feed in an image of a cat and it finds a bunch of cats. And so Peter took the same machinery, and again, say you feed in a number 4, you can find a bunch of other handwritten number 4s. You feed in a signal that you're interested in, and you tell it, go throughout the whole data set and find the signals that look similar to this input signal. And so it spits the best match out on the right, and you look closely at that and you realize that's the input signal. So you put it in, and it said, I found one that looks really very much like the one you gave me. And it is, in fact, the one that we gave the algorithm. So that's a good thing. It found the thing that we input. And then it found a bunch of other things that look like that. Why is this interesting? Because if you have a signal that you know is radio frequency interference, or that you're pretty confident is radio interference, and you say, go and find all the other examples of this in the data set, then you can help shovel some more of that haystack out of the way if you can pretty confidently label these things as being RFI. Another student of mine, Ben Jacobson-Bell, has another paper recently out where Ben is now not using kind of the fancy autoencoder stuff. He's just measuring properties of these signals. And so he's saying, what frequency is it at? How much is it drifting? How bright is it? And he measures actually 13 characteristics of these signals. And then he does this sort of like paint blob plot in the middle here again, is showing this embedding space where things that are close together are similar. So number 4s would appear together. If they're handwritten numbers, number 5s would appear together. And so these clusters in this embedding space are things that look superficially similar. And again, Ben's able to deploy this on the data set and say, okay, I now have some class of signals here. And you look at all of these kind of squiggles on the right here, and you eyeball them, and you're like, yeah, those look like that's the same phenomenon. And I forget which one I picked here, but there's some of them that we're pretty confident are GPS satellites, for example. So now we can say, okay, we're going to take all of the signals from GPS and just throw them away. And what's left is going to be potentially more interesting. We're also working with colleagues at the Allen Telescope Array, and so you drive a few hours north of Lassen National Park, and the ATA is a good test bed. We're working with folks at NVIDIA. You see Peter's face popped up again there. Another young engineer on the team, Luigi Cruz, and they're working on a real-time search. So here we got the signals from the telescopes coming in. I mentioned the data rate, so 1,000 times what's coming in through your home internet, even when it's maxed out. And so taking that and processing it in real time is really hard. We do a lot of our processing offline. They developed a system that can find, in this case, pulses from the Croft pulsar, but we're confident we can extend this to look for signals that might be interesting from a technosignature perspective in real time using this compute hardware from NVIDIA. And it's machine learning based, and so it's training the algorithm, just spot things that look like the thing that I'm interested in, and then spit them out when you see them. Okay, do I have a few minutes or? Okay, great. So I want to kind of switch gears a little bit and take us back to that transiting exoplanet that I showed you at the beginning. So the light dipping as it passes between us and its parent star. And again, we have a rich data set of these transits from Kepler and TESS, from those missions in particular. And I mentioned briefly earlier in the talk as well, how about a Dyson structure? How about a megastructure in orbit around a star? Could we see something like that? And again, this is way more advanced than what we can do with our early 21st century technology. But if you think back to the Drake equation, right? Remember, n equals L, right? Again, if you're an optimist about the possibilities for life and technology. And so let's say I'm going to do a survey, right? Think back to my my snow leopards in the Himalayas, right? If I stick my head out of the tent, on a Monday morning and there's a snow leopard staring me right in the face, I was going to say I'm extremely lucky, maybe I'm extremely unlucky if it's staring me right in the face because I'm breakfast. But if I see it right there and then I look around and it's like, wow, there's a ton of them, that means snow leopards are common, right? If it's easy, if you get your result on day one, that means there's lots of them. And so if we turn that, n equals L around and say, okay, if n is a big number, right, which means that SETI is relatively easy, so SETI succeeds, then L must be big. Conversely, if SETI is hard, and we do this, for another 20 years and we find nothing, then maybe that's because L is small, or maybe it's because, those fractional numbers, the chance of life, the chance of intelligence, maybe they're small as well. But if it's easy, then it's because L is large. And if L is large, that means that civilizations are long-lived. It means that technology is long-lived, which means that if SETI succeeds, we're not going to find somebody who's had technology for 100 years. We're going to find somebody who's had technology for 1 million years. I mean, let's say n is 2 million. That means L is 1 million on average, right? So if there's 2 million civilizations in the galaxy right now, they are on average 1 million years old in technological terms. And that's why it's not that far-fetched to imagine that they might be doing things that kind of seem like magic to us in terms of the engineering that they could do. So again, we should look for stuff like this just from a perspective of, how common they might be, and also the long timelines that are available. If intelligence got started somewhere else relatively early, then they've had a big head start on us. And this sort of got quite a bit of excitement around 2015 when a colleague, Tabitha Boyajian, at the University of Louisiana, found this star with the help of some amateurs who were looking through light curves from Kepler. That's now known as Tabby star or Boyajian star. And it has these really weird dips, including the one shown on the bottom right there, where it suddenly drops by about 20% in brightness over the course of just a few days, and then it returns to normal again. And, stars do dip in brightness by 20%, but if they do that, they tend to do that in a periodic way. And the weird thing about Boyajian star is that it looks like it's gone a little nuts. It'll dip, and then it'll return to normal, and then it'll have this kind of other strange behavior dipping by a few percent. And it sort of pushes the limits of models of things like swarms of comets in orbit around stars, protoplanetary disks, other things that could come between us and the star, blocking its light, and lead to these sort of strange kinds of variability. And so for a while, there was some musing, maybe it's an alien megastructure. And again, taking you back to, I don't know, slide number 5 or something in the slide deck, aliens should not be your first explanation. It's probably something else. Don't go running to aliens as an explanation. But it's still interesting to think about, well, like, could we find a genuine Dyson structure, and what would that look like? And so we've had some colleagues doing some work on this. And again, this sort of machine learning infrastructure. So this is another kind of representation of that autoencoder on the left there, right? On the left there, yes. And on the right-hand side here, you see, is that me? Okay. I was worried that I was like picking up the feedback from the speakers. So you see on the right-hand plot, so there's a series of shapes here in the second column from the right. And so John here fed in these shapes into a model, trained an autoencoder on it, and then said, predict what shape caused this. And he gets something that looks roughly the correct shape out on the right here again. So, again, if you feed in a number 4 and you get a number 4 out, you're pretty confident that your autoencoder, that your representation in the sort of, in the computer brain, if you like, is correct. And so that's what then enables us to feed in other light curves. And so you've got, a plot of how bright the star appears over time, and have it reconstruct some shape that maybe is not one of the shapes that you'd input, right? So, what would a giant triangle look like going between us and a star? Would it look a little bit like the one on the top? What would, I guess there's another triangle on the bottom there, what would this sort of, I don't know, hourglass shape look like? It would look like that one in the middle. And so we can then take a light curve and reconstruct an unknown shape from that. And if it deviates dramatically from circular, which is what you'd expect from a planet going between us and the parent star, then it's potentially interesting. And again, probably not aliens. You need more evidence for that, but it's a good step on the way to kind of look for these things. And you might find, some weird stellar behavior on the way. Whatever Biogen star is, it's interesting. It's interesting from an astrophysical perspective. We had another student, Anna Zuckerman, now in the graduate program at CU Boulder, and she looked at some Kepler light curves. And here she's looking at individual transits and saying, initially we thought, what happens if a transit goes missing? A star is, it's got a planet going around it, and suddenly that planet doesn't appear to be there, or maybe the transit's been cloaked, with some laser technology or something. I don't know, but let's go look for these because we have this rich data set of light curves. And so Anna went and looked at this. She looked for missing transits. She looked for transits that had, changed shape from their expectations. Again, nothing particularly convincing or outstanding. And so, we got a paper out of this, first author paper from Anna, published in the Astronomical Journal. And this is interesting. It's interesting both from point of view of the technique, but also from a point of view of, like, there's nothing so far that we've seen that doesn't appear to be just kind of vanilla astrophysics. Some of it's maybe some of it's like chocolate chip astrophysics or rum and raisin astrophysics, right? But, there's nothing out there that is not sort of explicable by natural astrophysical explanations. There's no clear signatures of aliens, and that's weird. I hope some of you at least are convinced by now that that's a little bit of an odd result. So let's come a little closer to home. So this is one of the Pan-STARRS telescopes in Hawaii. So one of the precursors to Rubin, and a lot of you have heard about Rubin over the past couple of days. I am going to touch on that before I wrap up. But Pan-STARRS was this survey looking for, among other things, objects in our own solar system, particularly potentially hazardous asteroids that might impact the Earth. And one of the things that it found was this object. So here you're looking down at the plane of the solar system, and you're seeing this orbit of this thing that's coming in and then exiting the solar system here around, first detected around 2017, I think, when it was in the inner solar system. And it's on this really weird orbit. It's highly inclined, and it's also hyperbolic. And the interesting thing about a hyperbolic orbit is, this is not gravitationally bound to the sun. It's something that's come from outside of the solar system. And so they called this thing, the telescope was in Hawaiian, so they gave this object a Hawaiian name, Oumuamua, which essentially means scout in Hawaiian. It's sort of somebody who goes ahead of the rest of the party. And so this was the first one of these interstellar objects that was found by Pan-STARRS. And so there's now 2 of them that are known. There's Oumuamua and another object called Borisov, named for its discoverer. you know, it's not unexpected that we should find things that have traveled between the stars in the solar system. But, you know, it's hard to find them, and there's only 2 examples that are known so far. Now, you know, it also, when people looked at the light curve, so you're looking at how this thing changes in brightness over time, they realized it looks pretty elongated. It's kind of a weird shape. This got some of our, perhaps more kind of, let's say, press-engaged colleagues talking to the press about maybe it's an alien spaceship, right? It came from outside the solar system. It's this sort of this elongated shape. To be clear, I don't buy into that. You know, and some very esteemed colleagues were sort of pushing this theory. I don't think it's a spaceship. Oh, yeah, there we go. So some of our colleagues at Harvard University, you know, very distinguished with lots of papers to their name. It's not always aliens. It's rarely aliens, right? You need a lot of proof. Extraordinary claims require extraordinary evidence. So, you know, we're still we're skeptical about this. But you know, here's another example of something in the solar system. It's the little red dots around here. Here's a multiple exposure of this object. 30-second exposures from a pretty small telescope in Australia. And over sort of 20 minutes, this thing is seen to move relative to the background stars. People find comets and asteroids all the time. When they do, and when they determine an orbit for them, they submit them to the Minor Planet Center. And so here's a bunch of observations submitted to the Minor Planet Center. And then the Minor Planet Center puts out these electronic circulars, and it says, we've given it this identifier, 2018 CN41. It's now in the catalogs if anyone else goes to look it up. This is common. This happens all the time. What happens a little bit more rarely is, oops, here's a retraction. We're going to delete 2018 CN41 because it turns out to be Elon Musk again with his space Tesla. So, you know, oh dear, you know, a bit of an embarrassment, right, to have submitted the Tesla to the Minor Planet Center and have it be given an identifier. But I think this is actually kind of cool. I mean, actually, I think kind of launching the Tesla into space is kind of cool. I watched the video. I thought that was kind of fun. But this is a technosignature, right? We found Voyager 1 using the Green Bank telescope, and now we found the space Tesla using, you know, an optical survey. So we can find technosignatures in the solar system. This is cool. I'm pretty sure there's not a Death Star in orbit around the moon. I think many of you would have spotted this if it were there. I'm not so sure that there's not something maybe that looks a little bit like a Oumuamua that's maybe hanging out in the asteroid belt or maybe out in the Oort cloud or something. Like, I'm not sure we would have spotted this. And we actually have a student working with me and a colleague, Chris Lintott, in Oxford this summer, trying to figure out, well, what could be hiding out there? Could we hide something like this in the asteroid belt? Can we simulate this and see if it should have been picked up by any of these existing surveys? So technosignatures in the solar system, kind of interesting. And I wanted to show this animation. I'm just going to look at my notes here because I have some notes about what's going on here. This is a simulation from some colleagues at well, his name's going to pop up, University of Rochester here. So what we're seeing here, these little pink blobs, it starts with a single system. So this is a simulation of stars, you know, rotating in our galaxy. And each of those systems, every 100,000 years, launches a rocket. And the rocket is just a standard chemical rocket, you know, speeds of 10 kilometers per second, so akin to Voyager 1, and they can travel no more than 10 light years. When they land on another world, the technology there persists for 100 million years and then dies, but it's replicating and it's sending out more probes. And, you know, just like everybody's familiar with this, having lived through the pandemic, you know, the idea of exponential growth, that we started off with just a handful of systems. And when this simulation stops 1 billion years in, technology is everywhere, right? And again, this is with sort of nothing much more advanced than the technology that we have. I mean, okay, interstellar travel is hard, but it's not requiring warp drives or anything like that. And so, you know, again, I take you back to the Fermi paradox. Where is everybody? If you've got a 1 billion year head start and you can, you know, seed self-replicating probes, these sort of von Neumann probe type things onto other worlds, then the whole galaxy should be full of these things within 1 billion years. So we got to look for them. Now, you know, I put this slide up a week ago. Maybe you wouldn't be as familiar with this. This is the Vera Rubin Observatory, and it has the world's largest digital camera, 32 gigapixel camera. This is the world's largest camera lens. It's got the world's largest filters. It's really amazing. It's going to look at 17 billion stars, 20 billion galaxies. Here's a little bit from the Rubin first look image. If you haven't seen these, go look at them on the web. They're really incredible. They were released yesterday. So much detail, I mean, really for all kinds of astrophysics. And it also has found in the first 10 hours, so this is going to start Rubin first look. These videos are available online too if you didn't see the press conference. So it found a bunch of moving objects, right? Here's an asteroid, and it's moving relative to the background stars. Here's another asteroid. Found that one too. Here's another asteroid. It finds a bunch of asteroids. In 10 hours of observing, it found 2,100 new asteroids. Okay? So this thing is like a solar system machine. It's going to find millions of them in 2 years. So it's going to be like an asteroid production factory. And so these are just the ones that it's found, you know, night 2, night 3, you see the numbers there at the bottom. This is pretty wild. And these were all, as you would expect, submitted to the Minor Planet Center. I think 5 of them were already known, it turned out, because since they did the observations and did the press release, 5 of them have been discovered by other people, but still they think that pretty much all of these are genuine. Probably, hopefully none of them are. Well, it'd be fun if some of them are technosignatures and they're not, you know, Elon Musk's car. But you know, you can see again the idea here, right? We should use this for doing technosignature searches. So we had a meeting in Oxford last year. The Guardian wrote a paper about how Rubin's going to be really cool for looking for technosignatures, you know, and it's going to be cool for finding interstellar objects too, like Oumuamua, even if they're just natural astrophysical things, they're still really interesting. We have another student in Oxford. Brian was a summer student working with us a couple of summers ago, and he has a paper. Can't really kind of make out the plots here. It doesn't really matter particularly, but you now should be familiar with the idea that I'm showing you a bunch of plots where we have a simulation and a reconstruction. And so Brian's made these models, which essentially are saying, you know, take the orbital eccentricity, take the semi-major axis, take the colors, take all the parameters that we know about these objects, and simulate them and see if you can get, you know, you plot up, you know, the radius of an orbit versus its color, which is one of these plots on the left here. And you say, okay, I can reconstruct that. And I can do that using a couple of models. One of them is using something called a Gaussian mixture model, and the other one is our old friend, the autoencoder. And then Brian can say, okay, what is the loss score basically again here? Like, how bad of a job am I doing at reconstructing this? And if you imagine again those handwritten digits, right, 0 through 9, if somebody feeds, you know, a letter X into there, it ought to stand out in that latent space, in that clustering space. The X ought to be somewhere else from all the things that we know. And so we can look for the anomalous stuff. And what Brian's showing here is he's got 2 anomaly scores on the plot on the bottom right here. So one from this Gaussian mixture process, one from the autoencoder. And then there's a few things that are circled in red where one or other of these models says, this thing looks weird. It doesn't look like the stuff that you trained me on. It doesn't look like the stuff that you fed in. Same reason why your bank calls you, you know, when you crop up in, you know, the north of Scotland and try and pull some money out of the ATM. They're like, this doesn't look like you. You're not normally here, right? This is an outlier. And so Brian's able to pull out these anomalies, and he was able to find, this is from the simulations of what Rubin is going to see. So the solar system simulations, he was able to find the interstellar objects that they put in the solar system simulations. He's able to find known families of asteroids and say, yeah, I'm pretty sure those are main belt asteroids, those are Jupiter Trojans, you know, pull all of those out. He was able to find some problems with the simulations that he later called up the team and said, oh, you need to, you know, tweak this and fix these issues. And so, you know, we're really excited about now that Rubin is coming online, instead of using the simulations, feeding the real data in, and hopefully it'll find more of these interstellar objects, and maybe even find technosignatures, which would be, you know, really, really pretty amazing. So just to wrap up, you know, again, around the time that Frank was doing those first experiments, there was this theoretical paper from Cocconi and Morrison in 1959. They said the probability of success is difficult to estimate, but if we never search, the chance of success is 0. You can find us on social media, including there's a pretty cool tour of the Green Bank telescope where if you do this on your phone, you can move your phone around and kind of ride with us as we go up the diagonal elevator that takes you up to the feed platform about 400 feet above the ground. We'll talk you through you know, the equipment that we have there, the receivers that are up on the receiver platform. So definitely check that out on YouTube. And then I mentioned our amazing young people that are working with us. So this was our crop of summer interns. We have 10 undergrads working with us at UC Berkeley. We took them up to Lick last night, and they got a cool behind-the-scenes tour of Lick, which was really fun. They're going on to do great things. They're ending up in grad programs and writing papers. And so if you have any smart young people in your family that are interested in a summer internship, our application's open in early December. It's not looking great in terms of kind of the funding environment for undergraduate research programs, over the next couple of years, but we're hopeful that we can maintain this and still have some cool summer programs and get other people excited about the work that we're doing. I think it's probably time that I wrap up, and I'm happy to take some questions.
Thank you, Dr. Croft. Okay, real quick, I'll bring the microphone around. If people on Zoom have questions, you can either put it into the chat or raise your hand, and I'll have you open up your, or unmute yourself.
All right, two questions. One of them is, how do you know that tecto signature from Elon Musk's car wasn't actually an alien because Elon Musk might be? How do you know? Okay, my other question is, do you believe that the hominid form, if there is technological life out there, that the hominid form might be optimal for tool making and for the production of technology? 2 arms, 2 legs, a certain height. Thank you.
Thanks. The first question I know was a little bit tongue-in-cheek, although they did match up the orbital parameters to the launch of the Tesla and sort of were able to figure out, okay, this is actually where we expected it to be. So we're pretty confident. As to whether Elon Musk himself is an alien, maybe the jury's out on that. But the second question. I'm not an anthropologist. We have talked to some anthropologists. In fact, we had some pretty cool meetings in South Africa with the anthropology sort of umbrella organization down there, thinking about, what is intelligence, what is tool use, how could we sort of assess, how common this is. I don't feel qualified to speak on whether, the hominid form or bipedalism or bilateral symmetry or any of those things are necessary. But one of the nice things about looking for technology rather than biology is that we're sort of agnostic as to who the producers of that technology are. So, if there's some post-human AI civilization, self-replicating probes or whatever that are out there, then we could pick up signals from those. And one interesting point that I didn't cover in this talk, but there's one world in our solar system with biosignatures, and that's Earth. But there are multiple worlds with technosignatures. So you point the Green Bank telescope at Mars, you see a bunch of technosignatures. They're coming from our own probes that we sent out there. But you point away from planets, you point at Voyager 1, there's a technosignature in the outer solar system. So technology has a tendency to spread and also be long-lived and also be unambiguous and also be kind of relatively bright. So there's a nice paper by Jason Wright from Penn State where he kind of talks about, like, should you put your money on biosignatures or technosignatures? And the idea there, I realize I've kind of strayed a little bit from answering your question, but if you go and do a search for technology, then you might find that it's abundant, and it might not even matter if the kind of progenitor of that thing was, biological or technological in the first place, or what its kind of body plan was.
Okay, I have a question from Kevin on Zoom. He says, what methods or instruments could scientists use today to check whether ET has actually already visited Earth and possibly left something of a token of themselves?
Yeah, that's a good question. So again, I point you to, I think it was Jason Wright, who I mentioned from the last paper. Jason does a lot of these kind of like big picture thinking kind of things. And I think that it was him, I may be misremembering who wrote this paper, but there's this idea called the Silurian hypothesis, which I think kind of comes from a Doctor Who episode, perhaps. And it's the idea that, the Earth may have been inhabited by some intelligent civilization earlier, and now, evidence has been wiped away of that. And they do some calculations whether, like, okay, how long would it take, if humanity went extinct tomorrow, for signs of our technology to persist? How long would buildings take to crumble away? Would there be any evidence left, in the geological record? And I think actually sort of one of the things is there might be some thin layer of maybe heavy lead ions or something that comes from the atmospheric nuclear testing, and that would be sort of the best signature that would last for a long time. So yeah, it's really hard to sort of see if anyone has visited in the distant past. But I think, if you read Arthur C. Clarke, then maybe looking for monoliths on the moon is a good idea. I do think looking in the solar system, is probably better than looking on Earth. I think if they've been to Earth and they've been elsewhere in the solar system, and if they're kind of hanging out, maybe they're monitoring us because of some prime directive kind of thing. I mean, that's another solution to the Fermi paradox, right? They're here, but they're kind of not interfering. Then these solar system searches are a really good way to go. So, you put forward your favorite sci-fi theory, put forward your favorite explanation for the Fermi paradox. I still think looking in the solar system is a good way to approach an answer to these kind of things.
So you said the Greenback telescope is in a quiet zone.
Yep.
Would it be better to be in the middle of the ocean? And also, people have talked about putting a radio telescope on the far side of the moon. So could you talk about those ideas?
Yeah, both of those are hard from an engineering perspective, and I guess the moon is harder. It's getting easier because the cost of launches are coming down, and actually, thanks to Elon Musk, if Starship works, which I think it probably will do eventually, but already, SpaceX has really brought down the cost of access to space with reusable rockets. And so if Starship can get substantial amounts of hardware to the moon, then it can get, radio telescope materials to the lunar far side. Building something that's 7,000 tons, like the Greenbank telescope, is going to be beyond reach for a long time. But you could build a low frequency array, of simple dipole antennas, for example. And actually, we're studying that. We have some funding through Breakthrough Listen to do a design study for what that would look like. And then building it is going to be a lot more expensive. But there the advantage is, if you put it on the far side, you have a few thousand kilometers of rock that's shielding you from all of the interference here on Earth. It's probably the most radio quiet place in the solar system. The problem is, as the cost of access to the moon is going down, there are going to be astronauts up there. There's going to be space stations in orbit. They're already proposing like an LTE cellular network for the moon. And maybe not everybody, some of our kind of geopolitical competitors might not be as willing to, sign the agreements that say we're going to play by your rules and, not do this kind of exploration so that you can do your radio astronomy or whatever. So it's cost prohibitive, basically, and I think sort of floating something in the ocean would be pretty cost prohibitive as well. And I'm not sure the ocean actually will be all that much quieter, because a major challenge for us now, again, is these satellites going overhead, including Starlink, which, again, the pros and the cons, right? You've got these reusable rockets, you can send stuff up there, and now you've got internet in the middle of the ocean. I've actually been out on a ship in the middle of the ocean where I was quite grateful to have access to my email, but that's not a great place to do radio astronomy anymore.
So I guess my question is, let's say you do make a radio telescope on the far side of the moon, and all the nations come together and we've got this great, collaborative effort. Mm-hmm. It seems like you have the techniques to get rid of the interference. Do you think your success of finding a signal is going to increase?
Yeah, that's a great question. And we've sort of done, even fairly recently, sort of somebody was asking, what's your sort of one wish for SETI? And, somebody said a lunar far side radio telescope. And I said, well, if you gave me, it depends on how big of a telescope you want to build, but let's say you gave me $100 billion and said, you can spend this on whatever. I wouldn't spend it on a lunar far side radio telescope. Instead, I'd go and hang around, somewhere in Silicon Valley, handing out $1 million checks to people as they left the offices at these AI companies. And I'd say, come work for us. We can't pay those competitive salaries with an academic group at UC Berkeley. And we've done some amazing stuff with primarily kind of student-led research, kind of deploying these AI techniques. And again, had some collaboration from folks at NVIDIA. That's been really great. But I think we need more kind of smart tech people who can write the algorithms. I tell our interns we may already have a signal that's sitting on disk, and it just needs you to write the code that's going to pull it out.
Hi, I just had a question. You had mentioned sometime in your speech here something about optimism, and I was just wondering, do you wake up like each day thinking, this is it, this could be it,
Yeah.
or we're going to find something, and sort of the opposite of that is as we progress and you find all these different ways to sort out the noise and everything else, is there any projection that, let's say in 100 years, if we haven't seen anything by that time,
Yep.
there's just nothing we can detect because of the distances or?
Yeah, no, that's a great question. In terms of optimism, I mean, I don't go to work every day expecting to find aliens, but I do go to work. I'm sort of cautiously optimistic, I guess. I mean, I think it's fun doing the search as well, and it's sort of an interesting result. I think particularly the solar system stuff. I mean, Rubin is going to be incredible. I mean, aside from the fact that, finding 2,100 asteroids in 10 hours is kind of nuts, and that's just a taste of what's to come, right, with the science that it's going to do. I think aside from that stuff that is, really cool from an astrophysical perspective, getting a null result out of that from a SETI perspective is also going to be really interesting. And sort of to your second point about, what if we don't find anything? I mean, the Fermi paradox becomes even more mysterious. And, I mean, maybe if you're doing sort of the snow leopard search, maybe you're sad if you don't see any snow leopards. And you could imagine sort of being sad if you find like, oh, we did all of this searching and nobody seems to be out there. But I think, the flip side of that is, if we're the only place that we know of that has life and intelligence, then we should take care of this planet. And that's a sort of good lesson to learn, I think, as well.
Right.
Maybe that's a good point to end, but I don't know.
More questions?
I guess this is sort of related to the last question, but I've heard this idea of the great filter, that it's hard or might be hard for civilizations to exist past a certain point. And just wonder, I guess that's more the pessimistic view.
Yeah, I sort of skimmed over this a little bit, but I talked about sort of hard steps in the sense of, you look at life on Earth, biology took hold really early on in life on Earth. Which suggests that maybe that's fairly easy. If you have ingredients and conditions for life, then single-celled organisms, come about pretty easily. And then the fact that it took, hundreds of millions of years for multicellularity, and then, hundreds of millions of years more for intelligence, maybe means that those are hard steps. And so this idea of a great filter being kind of some point, some difficult sort of stage that you have to get through, which then limits the number of intelligences that are out there. Is a consideration. And so this sort of question of, well, have we passed through a great filter already, which might be this hard step of intelligence or technology, in which case life is rare because getting to where we're at is hard, or is the great filter in front of us, which is kind of scary. And I alluded to that with the, Terminator robot in the Drake equation. Because as civilizations inevitably blow themselves up after a couple of hundred years of having technology, be it through, nuclear war, engineered pandemics, artificial intelligence, runaway superintelligence, whatever. Like, I mean, that's concerning. And so, maybe that sort of depends on how optimistic or pessimistic you are as to which of those scenarios you prefer, but we don't have an answer to that. One thing that is interesting, actually, so I had this Cocconi and Morrison quote, and another thing that I think maybe it was just Morrison that said, but he said SETI is the archaeology of the future, which is to say, you go out and you do a SETI experiment, you find out what happens to civilizations on average. Again, getting back to my point about, like, if Drake's L is large, then Drake's N is large, and so then we could be optimistic if we make a connection. If we make just one connection, then we should be quite pessimistic because it means they've wiped everybody else out and we're next. But there's various sci-fi books and movies with that plot too. But yeah, go to the Wikipedia page on the Fermi paradox is actually pretty good. They outline sort of a couple of dozen possible explanations, including some you probably not thought of.
I have a question. So hypothetically speaking, thought experiment. Let's say someday, maybe 1,000 years from now, we find a signal and we think it's an alien civilization, what happens next? And are we optimistic or pessimistic about actually contacting them?
Yep.
Will they wipe us out if they know about our existence?
Yeah. Yeah, so this is, I mean, a huge area of, post-detection theory. There are people thinking about post-detection protocols. What do you do? Who do you call? Those are actually in the process of being updated by a body under the auspices of the International Academy of Astronautics. So the SETI committee is coming up with some new rules that are a little bit kind of more up to date than get on the phone to the Secretary General of the UN, and are more like kind of put everything out on social media and, make the data available publicly over the internet and that kind of thing. So we certainly sort of strive for openness in terms of the science that we're doing. We strive for sort of communication with the world. We think this is an experiment that, that belongs to the whole world and not just to one group or to one nation. And then in terms of kind of, A, how the world responds, and B, how the transmitting party might behave. For how the world responds, in my mind, it sort of depends on whether it's kind of a single bit of information. essentially, we picked up a signal that, is a narrowband Doppler drifting signal, and it's coming from Vega, and, we called up the folks at the VLA, and they point their telescope at Vega, and they see it too, and then we called up the Chinese, and they pointed fast at it, and they see it as well. And, then we're pretty confident, we track this thing across the sky. Okay, there's aliens out there, but we don't know what they're doing. We don't know anything else about them. I think that's not going to be, an earth-shattering piece of news, given that probably 40% of Americans already think that we have proof of extraterrestrial intelligence. And so, a little bit extra, it'll be front page of the New York Times for a day or two. If it's the blueprints for, the warp drive, then I think, all bets are off at that point. And, in terms of kind of how things might go on from there, then I refer you to the three-body problem, Arrival, Star Trek. I mean, pick your favorite sci-fi. I mean, I don't have any more of an insight into that than sort of the imaginations of some of our great sci-fi writers.
Okay, just time for one. We'll do two more questions. I have one online, just asking if you could review the Amazon device for the home radio astronomy.
Oh, yeah. I don't have a picture of that on here. It is in another slide deck, so I won't try and pull that up. But if you Google software-defined radio, so an SDR, or if you Google GNU radio, GNU radio, and particularly if you combine those searches with astronomy, then you should be able to find that. I mean, I have, we've been very lucky because we have an expert from the GNU Radio Consortium, Danny Estevez, who has been doing in-depth tutorials for our summer students, maybe more in-depth than you would prefer, if you're sort of following along at home. But we have about kind of 10 or 12 hours of videos of Danny walking us through using these things, including some astronomy applications on our YouTube. It's actually the Berkeley City YouTube, but there's BSRC, Berkeley City Research Center Tech, and on our YouTube. If you Google GNU Radio tutorials, then or GNU Radio for astronomy or any of these, I can also send some of these links over in an email if they're of interest. And yeah, there's cool, build your own horn antenna to detect, neutral hydrogen in the galaxy and that kind of thing. They're kind of fun.
Related to what you were speaking about before, if we find something, what next? What about the theory that they're out there, but they're hiding because they're protecting themselves from us?
Yeah. Yeah, I think that's one of the ones that you'll see on the Wikipedia Fermi paradox page. Yeah, there's a few answers, and maybe was it maybe the Calvin and Hobbes cartoon. The surest sign that there's intelligent life out there is that none of it has tried to contact us. Yeah.
Okay, we are out of time. That was excellent, very engaging.
Thank you.
Informative lecture. Thank you so much for joining us. All right, we'll see you guys up on the mountain, and we'll see you back here next month. Clear skies, everyone.
Isn't it just pretty easy? We just look for old I Love Lucy.
Yeah, right. Yeah, or like the Hitler rallies being back at us.
Thank you again.
Yeah, thank you.
I was actually in contact.
Yeah. Yeah.
I'm a high school astronomy teacher.
Oh, cool.
I've persuaded the kid who's attending Berkeley is a freshman
Awesome.
to go in.